Every time your phone recognizes your face, every time ChatGPT answers a question, every time a self-driving car avoids an obstacle, there's a neural network making split-second decisions. But here's what most people don't know. These artificial brains work nothing like your actual brain. So what are they? And why are they suddenly everywhere? We're going to demystify neural networks for you in the next 15 minutes, and by the end, you'll understand not just how they work, but why some of the biggest myths about AI are completely wrong. Let's rewind to 1943. World War II is raging, and two researchers, Warren McCulloch and Walter Pitts, publish a paper that changes everything. They ask, can we build a mathematical model of how neurons in the brain might work? Their model was beautifully simple. Imagine a light switch that only flips on when enough of your friends push it together. That's basically what they created. A mathematical neuron that fires only when its inputs exceed a threshold. Fast forward to 1958. Frank Rosenblatt builds the perceptron, the first machine that could actually learn from examples. Feed it pictures of shapes, and it would learn to tell circles from squares. The media went wild. The New York Times predicted machines would soon walk, talk, see, write, reproduce itself, and be conscious of its existence. However, by the 1970s, researchers discovered perceptrons had serious limitations. They couldn't solve even moderately complex problems. Funding dried up. This period became known as the AI winter. But here's where it gets interesting. In 1986, a breakthrough called backpropagation changed everything. Scientists figured out how to train networks with multiple layers, not just one. Suddenly, neural networks could tackle problems that seemed impossible before. Still, computers were too slow and data was too scarce. Neural networks remain mostly academic curiosities until around 2012. Three things converged: massive datasets from the internet, powerful GPUs originally built for gaming, and clever refinements to training techniques. In 2012, a deep neural network crushed the competition in an image recognition contest, winning by a margin nobody thought possible. The deep learning revolution had begun. And we're living in it right now. So how does a neural network actually make decisions? Let's build one from scratch. Conceptually speaking, introducing the neuron. Think of a single artificial neuron as a tiny decision maker. It receives multiple inputs like pixel brightness values from an image. Each input has a weight, basically how much that input matters. The neuron multiplies each input by its weight, adds them all up, then asks, is this total big enough to get excited about? If yes, it fires. If no, it stays quiet. That excitement threshold is controlled by something called an activation function. The most popular activation function today is called ReLU, Rectified Linear Unit. It's dead simple. If the input is positive, pass it through. If it's negative, output 0. Think of it like a valve that only lets positive signals flow. One neuron is pretty dumb, but connect thousands of them in layers and magic happens. In a typical network, you have an input layer that receives raw data, say the pixels of an image. Then you have hidden layers where the real learning happens. Finally, an output layer makes the final decision. This is a cat, or this is a dog. Early layers detect simple patterns, edges, corners, colors. Middle layers combine these into more complex features, like furry texture or pointy ears. Deep layers recognize complete concepts, cat face. The network builds up understanding layer by layer, from simple to complex. No human programmer told it what cat ears look like. It figured that out from examples. So how does the network learn? First, it needs to know when it's wrong. Imagine you show the network a cat picture, but it guesses dog. We calculate the loss. The bigger the mistake, the higher the loss. Then the network asks, if I adjusted my weights slightly, would my predictions get better or worse? It takes tiny steps over and over across thousands or millions of examples, and gradually the loss shrinks and predictions improve. But here's the trillion-dollar question. In a network with millions of weights spread across dozens of layers, how do you know which weights to adjust and by how much? Enter backpropagation. After making a prediction, the network sends the error backward through the layers, from output to input. Each layer calculates its contribution to the mistake and adjusts accordingly. Think of it like a chef tasting a dish that's too salty, then figuring out which ingredient to blame. Was it the sauce, the seasoning, the base? Backpropagation traces the error back to its sources. This combination, gradient descent to find better solutions, backpropagation to efficiently update millions of weights, is what makes modern neural networks possible. Not all neural networks are built the same, so let's look at three major architectures that power most of the AI you interact with daily. Convolutional neural networks, or CNNs, are the image specialists. Instead of looking at every pixel individually, they use filters that scan across the image looking for patterns, like edges, textures, and shapes. Imagine you're looking for your friend in a crowd. You don't analyze every person pixel by pixel. You scan for distinctive features, their jacket color, their height, their hair. That's what CNNs do. This approach makes them incredibly efficient at image recognition, medical imaging, and even video analysis. Then we have RNNs, short for recurrent neural networks, which are designed for sequences, anything where order matters, like sentences or music. The clever trick? They have memory. Each neuron's output feeds back into itself, allowing the network to remember previous inputs. It's like reading a sentence. You need to remember the beginning to understand the end. If we say the cat sat on the, you're already predicting the next word might be mat or couch, using context from earlier words. RNNs do the same thing. They powered early voice assistants and language translation tools. However, they struggled with long sequences. It's hard to remember the start of a paragraph by the time you reach the end. Which brings us to transformers, the architecture behind ChatGPT, GPT-4, and most cutting-edge AI today. Transformers solve the memory problem with a mechanism called attention. Instead of processing words one by one, they look at the entire sequence at once and figure out which parts matter most for each word. Imagine you're reading. The animal didn't cross the street because it was too tired. What does it refer to? The animal, not the street. Your brain instantly connects it to animal by paying attention to context. Transformers do this mathematically, calculating attention scores between all words simultaneously. This lets them understand context across much longer passages, entire articles, not just sentences. They're also incredibly parallelizable, meaning they can train on massive data sets using powerful hardware. That's why they've become the dominant architecture in natural language processing. Let's look at three concrete examples of neural networks changing the world right now. Case 1. Medical image classification. In 2020, neural networks achieved dermatologist-level accuracy in detecting skin cancer from photographs. Radiologists now use AI systems to flag potential tumors in X-rays and MRIs, often catching things human eyes miss. These systems aren't replacing doctors. They're augmenting human expertise. A radiologist might examine 100 scans in a day. An AI pre-screens thousands, highlighting the urgent cases. The doctor makes the final call, but with AI backup, they're faster and more accurate. Case 2. Speech recognition. Remember when Siri barely understood your accent? Modern speech recognition systems achieve over 95% accuracy, better than human transcriptionists in some tests. They handle different accents, background noise, and multiple speakers. This technology powers real-time transcription for the deaf and hard of hearing, automated customer service, and voice-controlled devices. The breakthrough? Deep RNNs and transformers trained on thousands of hours of diverse speech data, different voices, languages, and acoustic environments. Case 3. Virtual assistants and chatbots. Many AI assistants you often interact with, they all run on transformer-based neural networks. They don't just match keywords anymore. They understand nuance, maintain context across long conversations, and generate human-like responses. A customer service bot can now understand, "My package hasn't arrived and I'm frustrated," and respond with appropriate empathy and solutions. These systems are trained on enormous text data sets, books, websites, conversations, learning patterns of human language and knowledge. The result? AI that feels surprisingly conversational. Before we wrap up, let's destroy 3 persistent myths about neural networks. Myth 1. Deeper always means better. People assume more layers equal more intelligence. Not true. Adding layers increases complexity and training time. Beyond a certain point, networks become harder to train and may actually perform worse. The sweet spot depends on your task and data. Sometimes a shallow network trained well beats a deep network trained poorly. It's about finding the right architecture for your problem, not just piling on layers. Myth 2. Neural networks understand context like humans. When ChatGPT writes a coherent paragraph, it feels like it understands. But here's the truth. It's predicting the most statistically likely next word based on patterns in its training data. There's no internal model of the world, no genuine comprehension. Show a neural network an impossible scenario, a fish climbing a tree, and it might generate a plausible-sounding but nonsensical explanation. It's pattern matching at an incredible scale, not understanding. This distinction matters. It's why AI makes confident-sounding mistakes, why it still can't truly reason about novel situations, and why human oversight remains essential. Myth 3. Neural networks are completely random black boxes. Critics often claim neural networks are inscrutable. You put data in, magic happens, answers come out, and nobody knows why. This isn't entirely true anymore. Researchers have developed tools to visualize what networks learn, which features activate specific neurons, which inputs influence outputs most, how decisions flow through layers. Yes, we can't explain every single weight in a million-parameter model, but we can understand the broad patterns. This layer detects edges. This neuron activates for faces. This attention head focuses on verbs. Neural networks are less random black boxes and more extremely complex, but increasingly interpretable systems. The field of explainable AI is making them more transparent every year. Let's crystallize what we've learned into 3 key insights. 1. Neural networks are pattern-matching machines. They excel at finding statistical patterns in massive data sets, whether that's edges in images, phonemes in speech, or word patterns in text. They don't think like humans, but they're incredibly effective at specific tasks. 2. Architecture matters as much as size. It's not about building the biggest network, it's about choosing the right tool for the job. CNNs for images, RNNs for sequences, transformers for language. Elegant design beats brute force. 3. AI is augmentation, not replacement. The most powerful applications combine human expertise with machine capability. Doctors with AI diagnose better than either alone. Writers with AI tools create more efficiently. The future isn't humans versus machines. It's humans working with machines. So from the first mathematical neuron in 1943 to the transformers powering today's AI, neural networks have come a long way. They're not magic. They're mathematics, architecture, and mountains of data working together. And they are here to enhance human life.